Hello, ladies and gentlemen. In this lecture, we are going to discuss Euler's method that is used to approximate the value of the solution of an ordinary differential equation. And this is a simple method and the numerical one used to solve ordinary differential equations. So given the form of the y, the x equal to f of x, y, it is particularly useful for approximating the solution of ODEs when an exact solution cannot be easily obtained, and the method works by using the slope of a function to step forward in small increments to estimate the value of the solution at successive points. And this is how it works. If you're given the function, which is now going to be f of xy with its derivative, then you need to know the initial condition. So the initial condition is always in the form of y x naught is equal to y naught. So we can use the method by looking at what is yn plus 1. So yn plus 1 will always equal to yn plus h into f of xn yn. Or if we are talking about yn, is always going to be yn minus 1 plus h f of xn minus 1 and yn minus 1. So when we substitute it in the value of the function, when we substitute it in the function, like xn minus 1, yn minus 1, we substitute them into the function times h, which is the step size, then plus yn minus 1, we'll be able to get the solution of that differential equation by looking at the nth iteration. So for example, if you are beginning with the values of the initial conditions x naught, then that means we can determine the solution of the ordinary differential equation. At that point, we will be able to find y1. So y1 will be equal to y naught. Okay, I'm saying y1 will equal to y naught plus h f of x naught and y naught. So in details, we are saying this is going to be the value of y at xn. H is the step size or the increment in x. F of x, yn is the slope of the function at xn, yn. So what are we meaning? If you have a function f of x and you have x values, if this is the slope, if this is the line of the function, that when we plot the values, for example, if we have x naught up to, for example, x1, here we'll have y naught, here we'll have y1. So if we are looking for the gradient of this curve, of this line, the gradient will be the y1 minus y naught divided by x1 minus x naught. But remember, the gradient is the same as the y, the x. Yes, the gradient of the line is always the change in y over change in x. Therefore, becomes the y, the x, a full derivative. So what is that going to give us? We can say here, this is going to be y minus y naught equal to, what is x1? x1 minus x naught is h. Yes, from here to there, it is an increment to x naught by h. So meaning your x1 is actually equal to x naught plus h. So y1 minus y naught will always equal to this dy dx times h. The h is x1 minus x naught. So, but according to Euler, we are provided that f of x, okay, if we take the value of the derivative, okay, the y dx at x naught, okay, so that will mean we will have x naught and y naught. This will be the dy dx that we are talking about. This is the y naught x naught. So what does that call us to do? If we substitute it back, we'll have y1 minus y naught, which is equal to h times f of x naught y naught. And if we look at it clearly, y1 will be y naught plus h f of x naught y naught. So now, if we talk about any value, for example, yn, so if we talk about yn and we are looking for the solution at the n, okay, this is going to be yn minus 1 plus h into f of xn minus 1 and yn minus 1. That will be the solution of the ordinary differential equation according to Euler's method. So let's go to an example. So this example is going to be found in the next lecture.